Good afternoon, everyone.
Good afternoon, everyone. Good evening, everyone.
Hello. Can everyone hear me fine? I'm not able to hear anything. Hopefully, everything is fine. Can everyone hear me now? I'll just wait for a few more minutes so that everyone will get. I'll just wait for 2, 3 more minutes. Meanwhile, we can have an introduction session. Like we can introduce ourselves. And I'm Rashi Rajanna. I'm doing PhD in IIT Delhi in Material Science and Metallurgy Department. I just want everyone. I want to know from introduction, a small introduction from everyone, so that I'll be understanding what exactly you guys are looking in this course and where I should be focusing more, and what is your if I know your background, I'll be teaching accordingly also. So, uh, Mithun can start. Okay, anyone can
Hello.
start then. Yeah, Mithun, yeah.
Mhm. Yeah, I'm Nidin. I'm doing PhD from VIT Vellore. Great
If
response.
it is fine with you, can you switch on your video so that like we can, I'll have a fair
Hello.
idea that, yeah. Only if it's
Okay.
fine with you. It's not a compulsion at the same time.
Okay. I
Yeah,
should know the
Mithun.
option.
Yeah, you're audible.
Yeah.
Okay. Someone else also can start meanwhile. I'm not able to hear Midun. I don't know whether you guys can hear or not.
Okay, good evening, everyone. My name is Arjun. Am I audible?
Yes, Arjun, you're audible.
Okay, just a brief introduction. I completed my mechanical engineering uh, undergraduate course in 2012. I'm currently working in a cargo airline called Blue Dart Aviation as a aircraft maintenance engineer, and I also specialize in structural repairs. Uh, but in my college days, although fracture mechanics, it was an elective, but I
Huh?
couldn't, I mean, were not offered. So now, after being in the field for almost more than 10 years, I realized that I should have a foundation understanding of fracture mechanics so that
Okay.
it will help in my work.
That's nice, Arjun. Arjun, I think so. You are the one who mailed me, right? Like regarding you had a question, something.
No, I didn't have a question. Actually, in our NPTEL Swayam group, there was a
Ah,
message saying that introduce yourself. So I had just given an introduction.
yes, yes. Ajay, yeah, that was your. Yeah, I remember reading about you.
Yeah, that's correct.
Yeah. Nice to meet you, Arjun. Yeah, next person, please introduce yourself. We'll try to start by 6:10 so that we'll wrap up the introduction by 6:10.
Hi, good evening everyone. My name is Lalit. I have done
I
my BTech mechanical engineering, and right now I'm working with a two-wheeler OEM. So my current role involves analysis of field failure parts, which most of time involves breakage. So I have joined this course to gain my knowledge into the failure mechanism, like how to analyze the parts, the metallic parts which have a breakage failure. So
Okay, that's nice actually. You're interested in mechanism, how the failure is happening, right? This is
yeah,
failure mechanics, engineering fracture mechanics. This is. So
right.
anyway, I'll try to bring up a little bit of that. I'll try to bring a little bit of fracture mechanism. I have a little bit idea. I have even done few projects in fracture mechanism analysis of how the fracture happened. So if it helpful, like I'll see, like in if possible, half an hour or so, anytime, like we can have a discussion regarding that.
Yeah, yeah, sure. Thank you.
Right down. Yes. Can anyone else go for introduction? If no one wants to introduce or anything particularly from the course, then I'll start with the teaching session. This is more like a introduction, and then we'll be just solving the assignment. And anything particularly, if you guys want, I will be noting it down, and then I'll try to bring up in further classes. As this is the first class, I thought of like usually we'll be doing just solving the assignments, the weekly assignments. That is how it is done. If anything particularly is required, you can let we know. I will add that topic in the next class. So like how Lalit was informing us that he wants to understand how the failure happens, failure analysis he want to do. So we can try to incorporate those type of things like for about half an hour in this session, in this 2 hour session. Anyone else? Or we'll start with the class?
Yeah, hi, this is Ramaya. I'm doing the
Yes.
PhD in Andhra Pradesh.
Where? PhD where?
NIT Andhra Pradesh.
Oh, okay. And I can appreciate so.
Yeah.
Your background is mechanical, sir?
Yes, mechanical engineering.
Okay. I'm a metallurgist, so I'll try to put more. I'll probably talking in terms of metallurgy more. Like, and if you guys need any help, especially in the field of metallurgy or anything, I'll be there to help you out. So we will get started with the lecture. And today's class, it's not exactly lecture, I would say. We will be solving today the whole assignment. It's anyway, you guys have been through week 1 classes, right? Everyone has gone through the classes, right? We have 3 lectures in week 1. Has anyone not gone through those lectures?
Yes, I have gone through it.
Yes,
Lecture.
I'm hoping like everyone has gone through it, and then we'll be solving assignment questions based on the first week lectures. So this is Rashi. By the way, I'll introduce again. I'm doing PhD in IIT Delhi in Department of Material Science and Engineering under Professor Jayant Jain sir. And as you all know, Ramesh sir has taken this course. He is chairperson at Department of Applied Mechanics in IIT Madras. And I'll be teaching based on his course only. I'll be doing a TA, teaching assistant for that course. And let's kind of have a brief introduction, like what you guys are expecting, and then what we'll be saying in today's lecture, in today's class. What is fracture mech? Why is the study of fracture mechanics is very important for us? Sir has already gone through very detailed and properly he has told us why fracture mechanics is important. And then I just want a couple of students, any one at least, to summarize why fracture mechanics is important. Can anyone volunteer? Why?
To make a fail-safe design, that is one thing.
Can you come again, sir?
Fail-safe design.
Fail what?
If you want to go for fail-safe design, the fracture mechanics is really required.
Correct, yes. And in general term, like anyone else can summarize further why the study was kind of important in the beginning, but how it even started.
For the life assessment
Seems to run.
studies, especially for the life assessment studies.
Hmm?
This
Yes, life assessment studies, correct. Perfect. Like when usually material was under some loading, they expected that it will last for a longer time. At least if started cracking or anything, it was expected that severe amount of plastic deformation will happen, and then only the fracture will happen. But that was not the case in most of the case study that sir has discussed, whether it can be Liberty ship case study or the Boeing one, the one aircraft one. We could see that the fracture happened in a brittle manner without even giving any further like alarm for us. Like fracture happened without giving any further alarm or without happening any severe plastic deformation. That's when actually the fracture mechanics became very kind of crucial. The study of fracture mechanics, they thought it is kind of important. So that's how it started. And the main motivation behind that was brittle failure at lower stresses in low strength steel. Like that was the even at lower stresses, as we all know, steel is something which should be able to withstand very high stresses, like comparatively in structural engineering materials. But then at lower stresses only, if they were able to see the failure in the form of brittle fashion. There was no proper plastic deformation happening or anything. That's why the fracture mechanics study kind of became very important, like to understand exactly what is happening in the material and how to avoid it and what steps can be taken in order to avoid it in future, or if possible even remove it. It is difficult to completely stop it, but avoiding is something that we has to be done. That's why the study of fracture mechanics kind of became very important. And sir has already showed. Sir has already shown that in 19th century, use of metals for structural application was like kind of severe. So understanding the structural material became very important. Even sir also mentioned that arts people were the one who were using like started to use all these structural materials. Excuse me.
The
Yeah, I would really request everyone to mute. So, as sir has already told before, the horseshoes were actually designed by art students. Like Leonardo da Vinci was the first person who made a shoe for the horse leg, and then further like optimizing when it came with the optimization, or when proper, like what type of material and how all these things has to be done, like which equation and all involved. That's when the science people, engineers and all got involved. But at the same time, many accidents kept on happening, whether it can be Liberty Ship one or any other further, even the molasses one in Boston. All these accidents led to the further investigation and then growth, the birth of the fracture mechanics to study the main branch again, to study how the fracture is happening. So these incidents we can these incidents actually led to make us understand why and how the fracture is happening, even though we expected the life of the material to be very long, but it was it couldn't serve the purpose. So the knowledge, whatever they had, was not enough. So in order to have a proper knowledge, like the design, the choice of the material, and like what type of material we are using and how it is designed, whether there are any sudden notches are present, or are we avoiding stress concentration region. Even though we do all these things, still the sample, I mean, materials used to fail. This is mainly because, like, people kept on forgetting the one point, that there are many flaws that are present inside the material as well. Can anyone tell me which one will be difficult to deform? Like, when to create a new surface, you'll be needing more force, or which is already having a crack, and then to propagate, it requires more energy to create. mm, to create a new surface, or to continue the propagation of the crack which is already present.
Already present.
Yes, which is all when the crack is already present, it doesn't need the much energy to break the bonds in between the atoms actually. So it can easily get propagated. Along with that, the stresses which will be present around the cracks will be very high. So this stresses will easily propagate through the sample, and then it breaks material faster compared to how with sample without having any defects. In our it is it is every time difficult to have an ideal material in the sense, it is always difficult to have an ideal material. Like, we cannot have any material without any defects and all. You cannot even assume that there will be no defects in the sample. Every time for sure, whether it can be voids or inhomogeneity, or whether it can be some type of inclusions during the casting, or any way, in any possible ways, like during the deformation. For instance, we do hot rolling very heavily, and then if oxides are forming, and then it gets entrapped on the sample, like it forms small, very minute crack. All these things will cause flaws in the material overall at the structural application. Obviously, these, when you put it under stresses or anything, obviously this material will not behave how it was expected. So it will fail in further sooner, because of the flaws that are already present. So, and further, the main important thing is like how the crack gets opened, and it depends upon how the stresses are acting near the crack region. So depending on that, there are three different modes. Mode one, opening mode. Mode two is whether it can be shearing or sliding mode. And then mode three is tearing mode. So further, we will see about all these things in detail. I just wanted to have a brief introduction and then give a fair idea about fracture mechanics, and we will little bit see what sir thought in last three class. Uh, and in the first class, sir was giving an introduction how studying of the fracture mechanics was important, and he gave brief history of the fracture mechanics, how it got developed, and how photoelastic effect is going to help us understand how the stress distributions are present across the sample when stresses are applied. And along with that, sir has discussed about the tension testing, and further he has also discussed about fatigue, little bit about fatigue he covered there. And then he discussed a few cases, that kind of very important cases back in 1900s, where how the fracture mechanics were got started, new branch fracture mechanics started, and why it became very crucial in back then. And then he also discussed a few case studies, which include pressure vessel, aircraft industry, as well as military industry. Like for instance, the ships where the ductile fracture was observed. And along with that, Sir has uh, shown the reason why it was happening, and then try to understand, and we kind of solve the problems, the case studies, and then try to understand from that point. And so, and we also summarized what are the things that we have to keep in mind, not neglect, even though it is right in front of our eyes. Most of the time we'll not even observe that, so observation can, it becomes very important. And then maintenance of the material, structural material also is important. So he sort of emphasized on these points, how observation and then the maintenance is kind of important, and also to have the knowledge how material behaves and in wide range of temperature. And for instance, even if you consider like other we have to consider other points like degradation of the material also, because if you keep any material in sun, for instance, and then you keep another material in a dry condition, one in outside, one in inside. Obviously, the one which is kept in outside gets more corroded, and then degradation happens. This is mainly because it can be because of rain or oxygen present in the atmosphere. All these things affects. Even though in dry condition, the some amount of oxygen will be present, but then it will not be accelerated because of other conditions like water or anything else. So material degradation also is possible with throughout the lifespan of the structural materials. So we have to keep these things in mind when we are designing materials, or when we are designing materials. And in automobiles especially, we have to consider one more point, fatigue of the material. Like for instance, yeah, I'll discuss more about fatigue later also anyway. So fatigue of the material also has to be considered, because result. So the fatigue of the material, how the fatigue is going to behave is how. So in automobiles, we have to consider one more aspect, which is fatigue, because when material is in tension or in compression, it behaves differently. Even if you apply a small amount of load, it is not going to deform much, or like it's not going to be very severe. So if you keep on applying fatigue, like if even the small amount of stresses are kept on acting on the same material with in a cyclic manner, whether it can be like very less load also, when you are applying in a cyclic, both in compression or tension, or it can be only in tension. Even if it is small amount of stresses, the material loses its integrity, and then it doesn't behave how it was supposed to behave. So this factor also will have to be considered when you're designing a material, because fatigue will also be present, and during fatigue, different you will be having material, it will be behaving differently compared to as that of tension and compression. So I hope this is clear. If any doubt is there, we can discuss meanwhile also. And little bit of more method. I can even discuss a little bit of aspects in on behalf of metallurgy as well. For instance, if you have a small amount of cracks on the surface, the fatigue can actually act very fast, and then it can can easily get initiated just because of very small crack on the surface as well. And then it can propagate compared to when you have a clean surface with like polished, and then where there is no roughness, very high, very low roughness possible. Then these type of aspects also matters a lot. And how is the microstructure of the material also becomes important when fatigue and this ductile to brittle transition temperature. All these things becomes very prominent. The microstructure of the material, how it is, whether it is homogeneous or not, all these things becomes prominent when you go in detail. So this is about the introduction. Let's go to the assignment one. We will solve one by one. And if you guys have anything else, like we can discuss now, or else we'll start with assignment now. I'll be sharing another one here, just to write here. So the question one says, in a perfectly rigid material, the value of Poisson ratio is what? Like they're asking for the. Uh, by the way, before we start next with the questions, do you guys have anyone has any questions like that has to be addressed? Yes. So I'll start with assignment topic if we don't have any other questions. So can anyone say me in perfectly rigid material, the Poisson's ratio will be what?
It is 0.
Yes, it is 0. I will still discuss a little bit about Poisson's ratio because this is kind of an introduction for whole class, and that's how I planned it for today. And we will be each and every question, whatever the possible background that we have to give, I'll give so that everyone will be able to understand properly. This first assignment one is kind of to have a brush up of on our basics. So along with this only, I'll not be just giving the answers directly. We'll be discussing the basics of that, and then we'll be going ahead. So when material, for instance, we are pulling any material in X direction, we consider if we are applying weights. Are you able to see the screen, by the way? I hope everyone are able to see the screen.
Yes, yes, ma'am.
Yes.
So like we consider that some amount of stresses is given in X direction, and we will not call it stresses only, but then anyway I wrote it as stress, so continue. And then it is getting elongated, and when it gets elongated, as you can see that there will be reduction in lateral direction, like in y direction there will be reduction in the material. There will be reduction in a cross section in y direction. So the Poisson's ratio will give us how up to what extent a material can get reduced in this direction, in lateral direction. That's the that's the point. That's what the Poisson ratio gives us the value. Whether it can be like when we apply it in longitudinal direction, the perpendicular to that one will become a lateral direction. So how much material gets deformed in lateral direction is what is given discussed by using Poisson's ratio. So when consider the material was like this before, and it got elongated to this direction, and it was initially length Lx. So what will be this length, by the way? If total deformation is delta Lx, so what will be this?
Delta Lx by 2.
Correct. So delta Lx by 2 will be, because it will be happening in both the direction. So if it is in 3D also, it will be happening in along the Z direction as well. Like the variation will be there in the length. Variation will be there in X, Y, Z, all three directions. And when we have to consider the strain of the material in x direction, what will be the strain? Then change in length, that will be the total length, how much it got deformed in this region as well as in this region, divided by original length. But so when you have to see how much it got deformed in y direction, you consider. So what will be in y direction? Can anyone tell me?
Delta Ly by Ly.
Is it positive?
No, it will be negative.
Yeah, it will be negative because it is getting reduced in that direction. So delta Ly, that's the only reason why I asked. That's all. And then in the similar way fashion, considering it is getting elongated only in x direction, so even in z direction also it will be having negative only. So surprisingly, when it is in this way, usually strain in y direction will be equal to strain in z direction as well. This is called lateral direction. In both the lateral direction, the resulting approximately around similar, considering that material is homogeneous, all those idealizing that it gets uniformly distributed, the stress is getting uniformly distributed, all those things. The strain that produces in y direction will be same as that of in z direction. Uh, and you can also see that the strain that produced in y direction will be proportional to strain that produced in x direction also. And in z direction, similarly, it will be proportional to x direction. This proportionality constant is what this proportionality constant is.
Poisson's ratio.
Okay, that's all. So usually Poisson's ratio is denoted by mu, and or like a few people will even say like write it in different, but then I use mu. So mu, like this is usually minus in lateral, whether it can be in x, whether if you are applying load in x direction, the lateral will be y and z, and then divided by the longitudinal. So can anyone tell me why there is a sign as negative?
Reduction in the other side. When it is elongated one side, other side it reduces.
It gets reduced, exactly. So there will be reduction in other side. In order to have the Poisson's ratio as a positive value, this whole everything they have just added minus here. That's all. So this is the reason why this is how the Poisson ratios are done. And considering for rigid material, it means that what it doesn't have any deformation at all. Like whatever the forces that we apply, it gets uniformly distributed, and we just study. We are under assumption that there is no deformation going to happen. So if there is no deformation going to happen even in x direction, so obviously there will be no deformation happening in y or z direction. That's why the strain will be zero, like in x direction, and the similar way in the strain in y or z direction also will be zero. That's why the answer for that one will be zero. And can anyone tell me what is the Poisson's ratio for most metals? What in which range it falls?
0.4,
0.4?
0.3 to 0.4, 0.3 to 0.4.
0.3 to 0.4, correct. For most metals, it will fall in point. What?
Madam, there is no such argument like no for rigid body again both delta z and delta x both are 0, 0 by 0. There is no such argument comes here.
Yeah, I don't understand the question.
For rigid body, that strain in all
Huh?
in the each direction it is 0.
Yes, strain
Yeah,
will in extra. Yes, yes.
when it is all the directions, it is 0. It is 0 by 0. There is no such argument here. It's
Yes, yes, it is 0 by 0. I'm just asking in metal, most metals, not in rigid body. I'm just asking in most material or in most metals how it will be present. Like what is the value of poisons ratio actually?
no, that's correct. Actually, coming to
Ah,
our question, the basic
okay.
question.
Yeah.
In the rigid bodies,
Huh?
in a rigid material,
Huh?
both delta x, both delta y, and all then
Yes.
delta
Everything
z.
will be zero. There will be no deformation in any direction.
Yeah. Okay. Okay. Thank you.
Then of course you guys know. Yeah. So anyway, continuing. For like, what does the negative value means in Poisson's ratio? Can anyone tell me like what does negative Poisson's ratio mean? Anyway, you can see it later and then let me know the what is the negative. So the answer is 0. It's correct. Coming to next question. In the case of combined axial bending and torsion loads, concept of yielding in material can be checked using. We will go. Huh?
See, theories of failure.
Theories of failure. So how many people
Tension
tell
test.
the how many are telling the theories of failure are correct? And tension test, who was the one who said tension test? Kiran?
Yes.
Ah, and
5 theories, sir.
yes, Suresh was saying something.
Yeah. You ask. There are 5 theories of failure. Is it?
Yes, there are 5. We will be discussing each one among them. Like we will see. I just want the answer now. Like I want to see how many agree with tension test or any other answers are there. Yeah, Suresh, what is the answer for this question?
Madam, I thought it is theories of failure. I'm not very sure.
Theories of failure.
I'm not very in case of combined.
How many accept with theories of failure is the correct answer?
I'm not sure actually. I don't know whether my approach is correct or not.
In the case of combined axial bending and torsion set, the onset of yielding in the material can be checked using.
Tension test.
Is it beam theory?
Huh?
Tension test.
Yeah, exactly. Tension test is the answer. So we will discuss anyway one by one how why tension test and not other answers. So if I'm wrong anyway, like you can let me know, like so that I'll go back and then I'll check if I'm right or not also. Okay. People please mute. Yeah, like someone has raised the hand. Like, am I? Am I? Okay, I hope that raising is not for the question anyway. So in beam theory, when we think that there is like kind of uh, some it's a free body diagram like for equilibrium and when some load is acting and in this direction some momentum is present, and if you have to find out what are the loaded forces acting or moments acting in particular point, we can find out using these things. We can find out using what is a bending moment or any other moment acting on any particular point or load. We can find out using beam theory. So beam theory will actually tell us at any particular point it should be in equilibrium. If forces are acting in one direction, consider in y direction some amount of forces. And in the similar way, if for that to be in equilibrium, even opposite direction also, there will be some forces acting in opposite direction, so that the point will be equilibrium. So the sum of the forces that acting on any point should be equal to 0. At the same time, even for the moment also at any point it should be 0. In the similar way, we can say that at point O, sum of moments from j equal to 1 to any number mj plus r into pi should be equal to 0. So these type of things we will be able to understand from Green theory, and how we will be able to get onset of yielding, where it starts yielding in the material. These things we will be requiring those points in later stage, but then in strength of materials it was required, it was taught, but in beam theory we will not be able to find out where the material is, whether yielding or not. Like we can only find out if the forces are 0 or not at any point there. That's all. So those are the things that we'll be able to find in beam theory. So in that we will not be able to find whether yielding in material is possible or not. And when we do tension test, what are the things that this is about the beam theory. And when we do tension test, we will be able to get stress versus strain diagram. Stress versus strain. Sir also asked us to write the numbers here, but then for time being, I'm not writing. I'm just writing the points that are important required here. And something like this will be able to here where fracture will happen. And this is the ultimate tensile strength. And this we can see yield point, and then lower yield point if we are lucky enough to see. So here we can understand whether yielding in material, we will be able to see whether yielding in material is happening or not, whether it can be in actual, like all the when it comes to yield point, the stress it yield point is a point where stress strain curve begins, which material enters the phase to non-linear region. Below this, it will be a linear region. It means to say that when you apply some amount of stress and then you remove the stress, and it gets back to its original position. So this is an elastic region. And in this region, Hooke's law will be proportional, where stress will be proportional to strain, and this proportionality constant will be Young's modulus. So after the yield point, the material will go into plastic region. It means that, like, even if you remove the stress, it is permanently deformed. It will not come back to its original position. So is it desirable for us, like for instance, any components in structural components that you have designed, consider that you some amount of stress you are applying, but then it is not coming back to its original shape and size. Is it a good thing for a component to have little bit of deformation in the material? Obviously not. So you don't want any deformation to happen in your material. So in order to avoid that, most of the structural materials will be operated well below yield point. That's the reason why sir has given this question, because yielding in the material is very important. It has to be understood very properly, so that it has to be even kept. The stresses should be kept in such a way that it is well below the yield point, and then so that whenever the material is loaded, it doesn't go back to permanent deformation. Rather, it will when we remove the load, it comes back to its original position. And that is the reason most of the material also will be considering yield point only for structural designing purpose. And one more thing regarding this tension test we'll be able to understand is once the yield point once the yield we'll be able to even see whether how much the energy or material can be able to store before fracture or before yielding. Before yielding, whatever the amount of energy which can be stored is called resilience, and up to fracture is called toughness of the material. So as much as we want the material to be present inside the yielding within the yield criteria, but at the same time we want the material toughness also to be very good. Like even by miss, if it goes to the plastic region, it shouldn't be in such a way that it gets fractured. For instance, of course we can even say that this is a very good ductile material, but then if it gets fractured without having much plastic region, it means that as you can see, the area under the curve here is in the first curve is higher compared to that of second curve. So the material can withstand only little bit amount of it can withstand only less amount of toughness, like it can withstand less amount of strain. It can store only less amount of strain stored in second condition compared to that of first condition. So we'll not be having much time to understand whether the material it will fail or not. Obviously, we have many things to consider, for instance, defects and all, the temperature, atmosphere, the operating conditions, all these things. At the same time, if you have a material which is not a very good toughness, then it means that it will fail the sample. Sample will have failure well below without even giving much warning to you. So as much as yield point is important, even the fracture point where it is present is also important. But then at the same time, not every time it will be ideal, like it will go up to fracture, it will very slowly fracture and all. No, it other conditions, the atmosphere, whether it can be corrosive conditions, all these things, where how the material is present, if any steps are present, all these things also plays important role in fracturing the fracturing the sample. So that is how why the theory of failure came. So in this, there are 5 different theory of failure. So we will see one by one. So consider when we are applying a load in tension, an amount of load, and we want this material. First thing is, as I discussed all these things, first thing, the maximum stress that a material can have, or material can have in the material will be the yield point. You don't want any material to go beyond yield point. So the maximum stress can be the yield point stress, whatever the stress corresponding to the yield point, that much amount of stress I can have. That is one condition, because as we know the reason for that. And then maximum strain in the material that we can have is at that particular, so this is corresponding to this one, divided by Young's modulus. This will be Young's modulus. Whatever the stresses are present at yield point divided by Young's modulus. That is the maximum strain that you can have in your material. And considering the total strain energy stored in the material, that is this resilience which I was telling. As you can see, it's kind of like a triangle. So if you take the area of the triangle, so the total strain energy that can be stored will be equal to that yield point square divided by 2E. E is the slope when it is in this, the slope of the curve. That is E, that is Young's modulus, by the way. So as you can see, it is approximately triangle. The area of the triangle is sigma y square by 2E. And then at the same time, for the similar condition, for yielding condition only, another condition we can have is maximum shear stress. And from previously we have, if you want, I can discuss in the next class also further about this, but it is always that when material is having stress in this direction, the maximum shear stress will be acting at 45 degrees actually. So maximum shear stress will be at 45 degrees. And that is given as, if you derive it, you will get sigma y by 2. And then the final one, which is the one which I forgot. Yeah, strain energy stored. Strain energy stored in the material will be sigma y square by 6g. If you want for these two things, we can have a derivation in the next class. For now, you can note it down. So as I have 5 different parameters: maximum stress, maximum strain, total strain energy stored in the material, strain energy, total strain energy and strain energy stored, and then maximum shear stress. So with five of this criteria, we have five different theories, theories of failure.
Madam,
Now you tell me.
Excuse me.
Yes.
The strain energy stored, what is the formula? Sigma y by
Sigma y square by 2g, 6g, sorry, 6g.
Okay.
So with five of this criteria, we will be having 5 theories of failure. So now you tell me how we will be able to find out yielding in the material using theory of failure. When further we will be discussing, of course, each and every theory of failure, like anyway. Yeah, I'll write it down here. So where did we even find out yield stress? I don't understand. So the tension test is the major point, how you will be able to finding yielding in the material. And fatigue also we will discuss a little bit. And bending theory will.
I don't understand. Actually, no. Can you please clarify in tension test how this bending and torsion loads are acting here?
Yeah, that's my same question.
Yielding in material is a material constant.
Okay.
So it doesn't matter. It gets transformed from elastic region to plastic region. It depends only. Doesn't matter whether you apply this one, axial or bending or torsion. The yielding will start happening. It's a material property that can be identified using tension test for all the material, as it is constant. Whether it doesn't matter whether you're doing in axial or bending or torsion. Yield strength of the material will be constant.
Bending and there is no bending and torsion loads. In fact, correct, no, madam? That understanding, is it okay from my side?
Can you repeat the question?
No, actually, in this simple tension test, there is no bending and torsion loads acting.
So, for instance, yes, you consider like we are having a material, and then
it's a pure
and you are
tension.
doing pure torsion. Consider a torsion.
Yeah.
So up to what point you can do torsion, and then when you leave it, it has to come back to its original position. It has to be still in the elastic region only.
Yes.
So you cannot twist completely, and then you expect and then you leave the material. It's not rubber. Don't consider rubber and all. Because rubber, if you twist a lot, it will still come back to its original position, because it's an elastomer. So it can stay. It can take more strain compared to metal. So for metal, we can only go up to yielding point, and then when we leave it, it will come back to its original position. Only up to certain stresses and strain only.
Can I understand like this? Whatever may be the case of loading, the yielding will be taken from the tension test. Whatever the yield point is it?
I have to probably see for that statement properly again. But yeah, yielding is a material property, and how like I have to probably see that again. I'll see it and then I'll let you know like whether, and if I'm not wrong, a little bit variation will be present in all bending also, torsion also, but then yielding will be there. Like yielding we can get it from tension test, and other tests also we can get it for sure, obviously, but we don't have those options here. fatigue text we cannot get, beam theory we cannot get, theory of failure, how you will be able to get in theory of failure? Let me know, please.
Okay, okay.
Can I add something here, please?
Yes, yes.
Okay, so I understood the same way how the earlier query came from a person. So actually here, what I understand is this question. What I understand is, in case if I load a rod in axial bending and torsion, it'll fail at a load lesser than the yield load, maybe 0.5 of its yield. Yes.
Uh, can you
Because of combined load.
Okay. Can you just tell me the question again, please? Like.
Okay. Here, what I understand, the question two is, I understand this is a combined loading. How to estimate the onset of yield in the combined loading where axial bending and torsion.
Okay, let me check that.
Let me complete, please.
Yes, yes.
Yeah. So if I just give only tension load, it'll fail at yield. Yeah, that is true. In case if there are more loads.
It is not true. It is not failing at yield. It is failing here, right? Fracture.
I mean, okay, for engineering purposes, yield is considered as a
yield, correct. For engineering purpose, yield for ductile material will consider yield point.
Yeah, so I'm restricting this to that extent. So,
okay.
If I subject the same rod for combined loading, including tension, yeah.
Yes.
So
yes, combined loading.
This will fail at much lesser value, or maybe 0.8 or 0.8 times of yield, not exact.
Correct.
So that's why I thought the theories of failure will provide at what point the yield will be onset.
Okay.
So
At
that's why I
what
thought
point?
theories of failure.
Okay, I'll check once regarding this one. I'll cross check it again. I got your point. At what whether it can be shear or like all these things has to be considered. That is true. So fine. I'll see this point again. Theory of failure or tension. Like I'll let you know in the we have a group, right? In that I'll type it tomorrow. Is that fine? Yeah, but still we'll continue with the theory of failure.
I wish to add one more point here. To some extent, I agree with Kannan, but the question exactly is like we are not quantifying the yield stress. We are just identifying the onset of yield. So probably identifying the onset of yield, I feel like tension test only the would be the right characterization methodology.
Exactly that because of onset was present even that is how the question was framed also, so that's why the answer was given tension test, but still I'll go through it again. I'll discuss with sir also, Ramesh sir also once, and then I'll give you the exact results answer for that. Okay, I hope that's fine. And then as we know, like can anyone tell me how the principal stresses and principal planes are like can if a material is under some stress, how to find out principal stresses and principal planes? So when it is happening in normal in one direction, whether it can be tension or compression or torsion in very simple one, simple loading, the complexity will not be there, especially when the complex loading will come. That's when the stresses keeps acting on keeps varying from point to point depending upon the even if you choose any material. For instance, we will see some complex loading happening in the material like this. So This is kind of little bit complex loading happening in different forces acting in different direction. And right now you want to understand at this point what is like stress, like principal stresses and principal strain. So this we can the on whether it can be at whatever the point it is, like in normal simple loading it is easy to derive the principal stresses or principal planes in which it will be acting. In this complex it becomes very difficult, so that's why we'll be having principal stresses and planes where it will be acting like in all direction we consider here. Just trying to have a little bit recap on principal stresses in strain. So wherever the shear value will be 0, so it consider be at this point, there'll be stresses will be acting in there will be infinite number of planes possible. At every plane possible, there'll be variation in stresses also. So this variation in stresses, like in so wherever the shear stress will be 0, in that particular plane, whatever the stresses will be acting, those are called principal stresses, and in which plane it is acting is called principal plane. So when stress is at 0 at any particular plane, then whatever the values we get, whether it can be sigma 1, sigma 2, and sigma 3, though those are called principal stresses and principal planes. I'm just describing this so that we will be it will be easy for us to discuss the theory of failure. And then the maximum shear stress will be every time it is considered that sigma 1 is maximum and then sigma 3 is the lower principal stress. So has not been. So when maximum shear stress, that will be sigma 1 minus sigma 2, 3 by 2. So when we apply these conditions for the previous thing which we have seen, 5 different conditions. So the maximum shear stress is possible is we can only go, it doesn't matter, like, so you can tell that the load applied here is like around 10 Newton and the area is very high, and then the stresses in overall the material is very low, stresses is acting well below my whatever yield strength. You cannot say like that, like at different points it will be having different different stresses acting. It doesn't matter about how much loading you will be put in. It also matters about, see, if any how the geometry is done, like whether depends upon the geometry of the material, and if any defects are present, etc. All these things will be mattering. So that's the reason. So when we said that maximum, in first case, the maximum stresses at any point in entire structural material that we designed should not go beyond sigma y. So the principal stresses, it means that and maximum principal stress, this is the first failure of theory, maximum principal stress theory.
Madam, sorry to interrupt you. This sigma 3, if it is if there is a one stress value is a negative value is there. If that
Yes.
will become the minimum, then can we consider that as sigma 3?
If it is in compression.
Okay. Yes.
Negative means it is in compression, right?
Yes. No, sigma 1,
Yes.
sigma 2, sigma 3. 3 stress values are there. The maximum stress value will be considered as sigma 1. The minimum will be sigma 3. Is it?
Okay, you are talking about whether if it is in negative, for instance, in minus 150, and then in tension it is 50 MPa.
Correct.
It should be it depends upon again like like even if you consider in opposite direction also, for instance you see here even if you
Yeah.
consider in opposite, like consider sigma 1 as 50 and then this one as 150 for instance, it will become positive 150 by 2, like it will be 200 by 2. So the 100, like my maximum shear stress will be 100 MPa only, no? Still, like if you consider the opposite direction also, whether it will be in shear will be happening in clockwise direction or anti-clockwise direction, that only matters, that only varies, right?
Yes.
Nothing changes much. So
Okay.
yeah, this is just a representation. Like whether it will be happening in tension, compression, or shear will be in clockwise direction or in anti-clockwise direction. That's all. When you see,
Let us suppose there is minus 150 is there, 50 is there, there is some other value is there. Let us suppose some 20.
so we should consider the maximum one as sigma 1 and minimum one as sigma 3.
That is a minus 150 and 50 only. The whatever the value in
Yeah.
between 25, that 25 should be need not be considered.
Is that will be sigma 2, right?
Sigma 2. Yeah, yes, that's what. That is the only doubt. Okay, ma'am. Thank you.
So maximum principal stress theory will be when sigma 1, we are here assuming that like sigma 1 is maximum, okay, for now. So sigma 1 should be equal to sigma y. This is for like this is how the maximum principal stress theory for theory of failures are done. And this is valid especially for brittle materials. And the second theory we had was what? Maximum strain theory. So maximum that strain, so second theory will be maximum So maximum strain theory will be what then now? Can anyone tell? Looking at the equation.
By Young's modulus.
By Young's modulus. That's all. Sigma 1 by Young's modulus. Whatever the strain that will be present shouldn't go beyond the maximum principal stress, that is sigma 1 or 2, 3, whatever is the maximum. It shouldn't go beyond maximum principal stress, and then it should be well below that. And this is kind of not used in much material, even though this is one of the theory, but not applicable much for any engineering application material. And then third is maximum shear stress theory. Can anyone tell me, just from the name itself, we can understand what is the maximum shear stress theory. So can anyone say me? And it's kind of, famous also. This is also
Maximum
called
stress should not
Theory?
this is also called Ruskin yield criteria. Yeah, someone was saying something. I'm sorry. I'm
I
really
told
sorry.
guest theory. Guest I told.
Just give me a minute. Yeah. So someone was saying something.
sigma y by 2.
Sigma y by 2. Yeah, that's how, like, yeah, as you can see here, maximum shear stress that it can go at, it will be at 45 degree and it will be sigma y, but then sigma y should be what then again, like sigma y is fine. That should be sigma y is the material. We have to work well below that material. But then in terms of principle, when you apply principal stresses, so I'm maximum anyway. I'll write it down. Maximum it can have is sigma 1 minus sigma 3 by 2. This is the maximum shear stress as we have seen here. that it can happen in the material, and this should not be more than sigma by y by 2, right? So it means that sigma 1 sigma 1 minus sigma 3 should be kind of well below, less than or equal to sigma y. This is the Truscan yield criterion. And this kind of uses, it's kind of famous in most of the material it is used. And can anyone tell me what is the next theory? Like,
Von Mises.
yes, von Mises theory. Just write it down here. This is also called as von Mises theory. This is kind of a little bit, it has few equations in this. We will just write down like whenever the stress is von Mises criterion should be equal to sigma y, and this is given as von Mises stresses at any particular load is given as and then sigma 2 minus sigma 3 by the whole square plus sigma 3 into sigma minus sigma 1 by whole square divided by 2. So that is the the whole square plus sigma 3 minus sigma 1 the whole square divided by 2. This is famous von Mises theory. And there is also principal stress, total strain energy theory, maximum strain energy theory also. For now, these two are important even for discussing the further questions. And fatigue test, when it comes to fatigue test, I'll just tell it down here, like, or I should write down here. I have not signed in this account, and it's kind of difficult to add new slide actually for me. So fatigue test, as I told in the beginning, continuous like variation in the stresses, maximum stresses and minimum stresses, we can keep it, whether it both the stresses can be in tension or both the stresses can be in compression, or some in one cycle the stresses can be in tension or compression. Like variation in stresses, like tension and compression we can give, and we can see how the material behaves. So consider, I'll just show one thing. So we will be expecting the material will be not failing. So if I keep on doing this pen cap, if I keep on doing applying very small load, if I don't try to deform like very much, then I can keep on doing forever actually. Even though some amount of stresses will be happening inside the material, but the it will not fracture or anything. So consider like I apply more load, and then I like very good amount of deformation I have given, and I'm getting it back, and then applying again, and then getting it back, and applying again, getting it back. It will break. It will not take much cycles to break the material, even though it depends upon how much stress you are applying. Lalit, you have some question?
Yeah, so I just wanted to know
Yeah.
the load which you are applying is will remain constant or it will be fluctuating
See, in
during the
not
fitting test.
in application, like if you see real application, obviously the material will not be constant. Will not be applying constant load. But for the sake of simplicity, for everyone, like even we, whichever the test we do it at constant load. like or at constant deformation, or like there are different type of tests also for fatigue also. But then yeah, the amount of load that you give will be kind of constant only. Yes. So that you'll be able to understand um the so that you'll be able to understand the how load is going to affect the material properties.
So is
Is
there
it
any test? Is there any test like in the fatigue test
Mhm.
where we can apply fluctuating loads because that more resembles with the practical application?
You can actually monitor that, but then why do you want? I mean, how do you even see? Like, you can for few cycles the load will be one particular condition, and for next few cycles the load will be varying. So, how you'll be able to understand the failure is because of the first load or because of the second load? How you'll be able to get the results? Are you getting my point?
Yeah.
So in order to simplify that, you can even do at higher loads and then continue doing the test and then see up to what failure and all, like what will be happening. And then you try to understand if I do it at this much load and these many cycles only will happen. So it's better like if I do it in a lower load, the cycle will be very long. So I I have a Lakshmi Narayana sir here in IIT Delhi who is working on fatigue. I can even ask them if they have anything that they can work in variation in load. But yeah, I can ask and I can let you know. But it doesn't. It we will not be able to interpret the results whether it is because of previous load or because of the present load. Yeah, Kanan.
Yeah, can I understand regarding this fatigue that yield doesn't play in fatigue related failures
Can
for
you
the
come
purpose
again?
of this question? For the purpose of this question, can we say that
Yes.
yield has no relationship or yield has no effect on the fatigue failure for any materials?
It has effect actually, like yield. He's like whether yeah, that will come. We will discuss later further in detail. But yes, yielding will be affecting actually. So whether the stresses at the concentration, like at the crack tip, whether it is in the plastic zone or in below the yield zone, well, that matters actually. Especially the when the stresses at the crack tip. So whether it is less well below the yield zone or above the yield zone, so that further propagation of the crack depends upon that. If it is above the yield zone, yield limit, yield stress, then the crack gets propagated, right? So yes, effect is there, but in detail we will discuss in further lectures. Yield stress, yield point is there, effect will be there.
Thank you.
It's fine. So where were we? So yeah, fatigue test. In fatigue test, we'll be able to only see that what are the stress amplitude that you have given, maximum stress amplitude, like whether it can be considered like this is around this is the stress amplitude that you have given maximum or the maximum stresses that you are applying. You'll be getting the SN curve, like how much is the stress that you applied and how many loads it is able to withstand. If you are applying very high stresses, it means that it gets broken very easily. So you cannot go in that region. Doesn't matter, even though it is well below the yield point, because of the stresses that is getting varied a lot, the fracture will happen. Even though you are applying the stresses well below your yield point, you cannot tell that like yeah, I'm applying the load or not more than yield point, why it has to break. No, because of the cyclic stresses it gets broken, as I just showed in this plastic uh, pen cap. It got broken even like by when I apply many number of loads, like, and then it kind of becomes even easier to break the material after applying load. Like if you have to break the material, like either in tension or anyway, like it even in bending moment also, it becomes difficult to break in only one applied. When you apply a little bit of fatigue and then try to break the material, it gets broken very easily. There also you can say that like the material is not I'm applying the load still well below the yield point. No, why it is breaking? You can ask the same question there also, right? You're getting my point? So the fatigue I hope I made the point clear. Even if you are applying the load well below the yield point, the fracture will still happen. It's only because it is the load is in cyclic mode. That's why the compression tension will be happening in the material. That's why it gets failed well below the yield point, well below the load that we applied in yield point. So I hope I made the point clear. So we will be getting the onset of yielding in material by doing tension test only. And I'll be checking about this later for sure. The theory of failure, because it's combined axial bending and all. But I'll once check it with sir, and then I'll let you know for sure. Like, but then yes, of the onset of yielding in material we can check using tension test.
It's clear, madam. Actually, only one thing, that whatever that von Mises, that formula you have written, no, that slide, can you just show me once? Show.
Von Mises, I can tell it down because
No, no,
it is.
You have written some in one of the slide. You have written, but that what's. Yeah,
This, I
yes.
think so this one. I did not actually sign in this one. That's why I'm not able to add new slide. I'm so sorry. Next
No, no,
time.
some others. No, some other slide you have written. Just we have. Yeah, here. Sigma 1 minus sigma 2 whole square. That is minus or plus before that sigma 2 minus sigma 3.
This is plus only.
Plus. Okay. 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 Please continue. Thank you.
So yeah, like usually von Mises is also used mostly, and then total strain energy theory also is there. So these are the 5 theories. Theory. In this one, like usual, I kind of forgot the formula. It is kind of very big, and then it's sigma 1 square plus sigma 2 squares plus sigma 3 square minus 2 Poisson's ratio into sigma 1 into sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma 1. And this should be well below the yield sigma y square by 2e. This is total strain energy theory, and usually it is for ductile materials. Plus sigma 2 square plus sigma 3 square. Sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma 1. Should be equal to or less than or equal to by 2e. These are for ductile materials. So according to Tresca's, next question we will go. According to Tresca's failure criteria, the material will fail when the maximum shear stress reaches. We just now discussed all the 5 theories. Are everyone able to see the slides? Is the slide changed?
Yes, we can see.
Yeah, so according to Tresca's failure criteria, the material will fail when the maximum shear stress reaches. We have just discussed all the theories, 5 theories, and Tresca
Half the yield stress.
After
Yield stress.
what is yes, like it is half the yield stress only. Sigma 1 by 2, it was there anyway. It is easy. So, and can anyone give this answer? Von Mises criteria, yield criteria, onset of yielding takes place when sigma 1, sigma 2, sigma 3 are principal stresses. Say that, and then sigma ys is a yield stress, they're telling. So what will be the von Mises criteria? What is the formula? It is straightforward.
Ma'am, this is question 4. So I'm seeing only question 3.
Oh, okay. Now?
Yeah, now it's okay. Yeah, thank you.
Yeah, I think so. There is a little bit lag. Please let me know whenever there is a lag. As we know, von Mises theory is equal to square plus sigma 2 into sigma minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square divided by 2. So they're asking that, so if we try to see it, sigma 3 square into 2. So this should be, it is given equal. Even we can consider it should be less than or equal. Whatever the stresses at any point, that should be the von Mises stresses should be less than or equal to the this one should be greater than. Should be greater than von Mises stresses should be greater than the principal stresses acting in the material. So this one will become greater than or equal to sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 the whole square. So when you shift it to that side, like it will become less than or equal to, so the answer will be C. Is everyone fine with this? So this less than or equal to sign or greater than or equal to sign is kind of very important. We need the principal stresses way lesser than our yield strength. So depending upon different failure from failure theories, we have different criteria also. So when so from this point, from fifth question, we just now discussed about fatigue. Everyone are able. I hope everyone are able to see the slide. So from fatigue, from theoretical standpoint, when a material is subjected to fatigue below the endurance limit, the material will dash like what? What is the endurance limit, by the way? Can anyone tell me? Can anyone discuss a little bit more about fatigue? Like Lalit, I think so. You are doing some fatigue test, no?
I give a guess, ma'am.
So can anyone tell me a little bit about fatigue?
Ma'am,
What
can I give a
exactly
guess?
is? Huh?
You asked us about the endurance limit, right? Can I add
Endurance.
something?
Yes, sure.
Okay. If I remember correctly, endurance limit is one below which there will not be any fatigue failure.
Will not have any fatigue failure.
Yeah.
Correct. That's true only. That is theoretically anyway. So yeah, anyway, yeah, theoretically was
Actually,
also given. The
actually
question
that
was, what
material,
is endurance limit? The question was that. I did not ask for the answer actually. Even though the answer is correct, I was asking what is endurance limit?
it is the maximum stress at which the material will not fail at all.
What is the maximum stress like where? Which maximum? I need proper answers. Like which maximum stress?
The maximum stress it can take for unlimited number of cycles.
You mean to say the cyclic stresses
Yes,
amplitude.
yes, yes, yes.
So below particular amplitude, the material will not fail when we are doing in cyclic loading.
Yes, ma'am.
Yes, correct. That is endurance limit, like that usually is seen in ferrous materials. So when we draw SN curve, or cycles, number of cycles in log scale. Both are in log scale. So we will be having somewhere like it will be starting, and then below that, consider this as a 0.9 of uh, uh, the ultimate tensile strength, or it can be yield strength also. Anyway, for now here, SU is ultimate tensile strength of the material, and S is the amplitude that you are applying, how much there is a cyclic stresses that we are applying. So if you are starting, consider like you're putting the cyclic stresses just near the ultimate tensile strength, of the material, then obviously even without having much number of cycles, you'll be having a breakage of the material. So the number of cycles are very low. So when you keep on reducing it, when it's around 0.9, when you're very close to the ultimate tensile strength. So with reducing the cyclic stresses well below the ultimate tensile strength, you can see that the life of the material is going very high. So if the number of cycles yeah, here, like here is very high compared to that of number of cycles here. And this stresses, consider it's probably a 0.8 of SU, or this is around 0. I don't know, 0.5 SU. I don't know exactly the values. I'm just giving a rough estimation here. That's all. So below this, this is called endurance limit, where the number of cycles are made very high. Below the particular limit, that limit is called endurance limit.
Madam, it is 0.05 SU or 0.0?
I'm just simply writing that. That is just a random number. This is endurance limit. So if you apply, theoretically, it is supposed to be, if you apply stresses well below the endurance limit, it should have an infinite life. But that's not the case, how it will be present usually. So anyone else has any other answers other than this one? I hope the question fifth is also clear. Yes, yes. Yes.
Actually, I recently learned that you are telling that this applies for ferritic materials, right? I just recently learned that the exception for this case is stainless steels.
Okay.
Just information.
I actually couldn't hear properly. Can you tell Kanan properly again?
Yeah,
it's Kanan, right?
Yeah, correct. Yeah, the endurance limit. You are telling that it applies for ferritic materials only.
No, only for this one, ferrous materials.
Ferrous materials.
Yes, it's only for ferrous materials, right? I'm right only, right?
Yeah, I mean, so stainless steels are also called ferrous. It'll be classified under ferrous materials, right?
Yeah, stainless steel also is classified under ferrous material only.
Yeah, but I recently learned that stainless steel does not have any endurance limit.
It is endurance limit is usually mentioned for ferrous material only, but let me check that point also. That question also.
Yeah, this is as per API 579. You can take a reference of this.
Yes, that will be better.
API 579.
Okay.
Thank you.
Anyone else has any question? Like I'm seeing the chat just now. Yeah, I hope nothing else. So I'll be moving to next question now. So common disaster failure underlines the importance of which of the following? Can everyone see the slide? Yeah.
Yes.
Yes. So common disaster failure, we have seen few failures in the material. Like we have seen few case studies. One among them was comet disaster failure. That comet disaster failure was which, can anyone at least tell what was the instrument, whatever the structural, what was comet actually? Did everyone see the lecture?
It was the first jet
Airplane.
aircraft.
Huh?
Yeah, it was the first jet trans
It was the first commercial jet, correct.
high speed. You can fly at very high speeds.
So that had what variation in material behavior with temperature. There was no much variation in temperature. Of course, like there will be variation when you compare with um, different places also, but that was not the reason why. That was not like underlining reason for the failure of the material. And the importance of stress concentration, stress corrosion, and design for corrosion prevention control. Like that was also not the reason. Like as I wanted to even mention that corrosion also is kind of very important. It not only just corrodes the surface of the material, it also makes a few pittings, like very small pittings will be formed. For instance, you consider there will be smooth material, soft, like roughness is very low and all. But then when corrosion will be happening, the corroded layer will be forming, starts forming like on the surface. So this usually the corrosion will be oxides. Just wanted to discuss few things. And then below that will be metal mostly. And then this, because of the corrosion, the oxide layer will be formed on the surface. And then when at the same time, if at all, if we have any other corroding or pitting reagent like chlorides, especially when you go in sea level or anything, chlorides will be also present at the same time. You know what these forms? They form a very small pit on the surface. And then it form because of the stresses present on the on the material. This very small pit will form a very thin crack. It will form a crack. And as you know, the stresses at the crack tip will be very high, and then it get because of stress concentration will be very high, and then this as the material will always be present under some stresses, it will get easily propagated. So stress corrosion cracking is also kind of very important, because like others you can see through the eyes, but then this pitting which will be present, you cannot see through the eyes. It is very difficult, like pitting corrosion on this type of, especially because these pittings will be covered by oxides that are surface oxide because of corrosion or something else. Usually that will be covered by oxides, corroded layers. That's why stress corrosion becomes very crucial, especially when you have other corroding agents like chlorides and all pitting agents. So, but then that was not the reason why the comet failed, right? That was the reason for Boeing 1. The crack developed in stress concentration zone and grows in service due to fatigue loading. As we have seen that the window which was there was well above the limit. Usually the windows that we have are very small in flight. So at this region, even if a small crack gets formed, this not only acts as a crack, but then this, yeah, even though the size of the crack is very small, this acts as like, as there is a hollows, like, hollow, that's why it acts as a very bigger crack, and then it gets easily propagated and then grows in severe due to fatigue loading, as the cabin will be under pressure and then pressured and unpressured. Because of this, it gets easily propagated, and then because of the fatigue loading, it gets it was failed mainly. So the C is the right answer. And when riveted joint acts as a crack arrestor, here the rivet did not come. This was coming. This was present in Liberty ship. And then structural health monitoring, including visual inspection. As the crack is very small, we cannot even see this using our naked eye or anything. So that was one of the reason. Like, so the crack, and the right answer is this one. If anyone else has any other thing in this question, we can discuss, or else we can go to next question. Whatever I said was right. And there's no saying less anything else. So the right answer is crack developed in the stress concentration zone. Yes, Suresh, you want to say something?
Yeah, madam, this importance of the points. Point B, the stress corrosion. This belongs to case, madam. Like you told, for riveted joints is for the liberty. Similar way, the stress
In
corrosion.
this one, the Boeing one, which was there, like you remember, like the and the corrosion was there, but
Aloha to Sa.
Aloha, correct. I'm sorry, Aloha one. Yeah.
Okay, madam. Thank you.
I think so, but still that flight was Boeing only, if I'm not wrong. Aloha one.
Yeah. It was a Boeing 737-200.
Yes.
1988.
Yeah, it's actually these case studies are very nice and very interesting to study also. So anyway, moving further. So yeah, for materials used in nuclear reactor, nil ductility temperature (NDT) changes are studied by placing the specimen inside the reactor. So we will discuss a little bit about, we have 20 minutes. Like we have still so many things to discuss. Anyway, okay, first. So nil ductility temperature is the temperature below which the material behaves like a ductile material, and then above which the toughness, in this case we'll be using toughness of the material, and the temperature. The toughness of the material is low. What can anyone say me why brittle material has low toughness compared to the ductile material?
With the plastic zone is very small. The overall area under curve will be small compared to.
In brittle material, the stress versus strain will be like this, and then it will fail here. That's all. And then in ductile, it will be here like something like this. So this will be brittle ductile material, and this will be brittle. The area under the curve for brittle material will be lower compared to that of ductile material. So the toughness of the material will be higher in ductile material compared to that of high. So with increasing the temperature for any material, it will be kind of like this. So the toughness actually shouldn't drop. If the toughness has dropped, it means that the material is not suitable for our application. So this region, the temperature below which this is the temperature, a particular temperature above the material will be behaving like ductile. The toughness will be very high, and below this it will be behaving like brittle. The toughness of the material will be very low, and there will be some region where the transition will happen. This region is called NDT, nil ductile temperature. Below this will be ductile material, above this will be so that this is true. And then this not just because of the temperature and other factors also will affect these conditions, even the microstructure of the material. These further things probably I'll discuss in the next class. I thought of discussing in this class only, but then it's taking so much time. For next time onwards, I'll try to I'll see what to discuss soon. So grain size of the material grain size, how the microstructure is distributed, microstructure, grain size, and then composition of the material, and whether it is what is that? What conditions? Whether it is in ideal condition where it is dry and all, or in radioactive condition, this atmosphere at which we are using the material also will matter. So the microstructure. So the microstructure of the material, microstructure, the temperature, the composition, and the atmosphere in which we are using the material, all these things will vary the nil ductility temperature. For instance, if we are keeping the specimen inside the reactor, in the nuclear reactor, it means that it is getting exposed to the what all the radiations present in the material. So the ductility, this one. So it gets shifted to right. Like, can anyone tell me why is the shifting to the right is a good thing or a bad thing, and why? Can anyone tell me this? Why? Can anyone volunteer to
It's a
tell
bad
me?
thing.
Huh?
It is not desirable, I think, because you will
Why
want
is
a
it not
metal
desirable? Why is it not
ductile.
desirable?
You will want a metal to be ductile rather than brittle. I mean, you want it to exhibit some plastic deformation before failure. Is that the reason? So
Arjun,
if the
right?
yeah, Arjun. So if the nil
Ah,
ductility temperature increases,
huh.
your metal will behave as a brittle material for a more larger range of a higher range of a temperature.
Range is same
So,
only. See, the range is same. Both the places range is same approximately.
but when the ND that nil ductility temperature increases, so
Huh.
can we say that the metal behaves brittle, exhibits a more brittle property for a larger temperature range?
Even at higher temperature, it will be
So it,
acting like a brittle material
so
only.
It's not
so
desirable
it's
actually.
not
Shifting right
desirable
is
for
not desirable.
Yes, yes, it's correct only. I was just asking you a question. Is whatever Arjun was telling was correct. Shifting of the curve to the right side is not desirable. If at all, if possible, we have to shift it to left side. So that is more desirable compared to even we do the microstructural changes, compositional changes, everything in order to shift the curve S curve to the left side, not to the right side. So radiation, because of radiation, it will be shifting to right. And then yes, for material in nuclear reactor, changes, the studies can be done in such a way we can keep the samples inside the reactor and take it in some time and then test it with different temperature and see whether the uh, what we will be able to see the entity at lower temperature at higher temperature. So the right answer for this one is true. Then, so now you guys answer this question. Nil ductility temperature for material in nuclear installation is dash. We will answer soon so that we'll go to next question.
A increases due to radiation exposure.
NDT increases. Yeah, correct. It's right on. The contours of constant color in photoelastic experiments are known as? Yes, come on. Even I thought of discussing a little bit.
Isochromatics.
Yes,
Isochromatics.
correct. Isochromatics. I thought of discussing a little bit more on photoelastic. Probably in next class, I'll discuss a little bit in detail about photoelasticity. But I am pretty sure you all are mechanical engineers and you guys are well know about all these things. But I thought of revising once the terminologies. So in the next class, we will first start with the photoelasticity and then we'll revise the terminologies and then we'll go to next topic. So yeah, for isochromatic. The bending stress is dash. Come on, this is easy one. Everyone should be able to do it very fast. Everyone are able to see my slides?
Directly proportional to distance of layer from neutral layer.
Yes. So I don't have to explain this in detail. We will see like what and all is required. So anyone has solved this question? We will do the solving now. The question will. Yeah, someone has something to tell?
Please solve, madam.
Yeah, we will solve this question. A circular component with AISI, it's a code 1080-1018 mild steel with ultimate tensile strength as 460 and then yield strength as 370 has to be designed. In such, find the diameter in mm required if the tensile loading has to be limited to 10 kilonewton with a factor of safety as 2. So just tell me one thing, which stresses will you consider? Just tell me that thing, that's all. Which is the maximum stress that you have to consider, whether
Yield point stress.
Yield.
Yes, correct. Exactly. That's the major point here. Even though UTS is given for us 460 MPa, and then yield stress is also given 370. But then as this is a ductile material, and we should consider only yield stress. So the even for creating for factor of safety, which is given as 2, we should consider maximum stresses, maximum divided by working stress. Maximum stress we have to consider is 370 MPa. And then as the factor of safety is given 2 divided by 2, so the working stress, the maximum working stress we can go up to 185 MPa. Right? So from this we have, and then as they have mentioned that the load that can go up to is 10 Newton. So maximum P max is 10 kilonewton, by the way. Sorry, not 10 Newton. So this is equal to force per unit area. And then they asked to find out diameter, right? So the area will be circular as it is a circular. So area will be pi r square. And the load that maximum that we can do is 10 kilonewton. It means 10 into 10 power 3 Newton divided by pi r square. And then as we know, this is equal to 185 as it is written in MPa into 10 power 6. As we know that Pascal is Newton per meter square. So all are in Newton, all conversion is done. So further, if you solve for R, we will get it as 4.15. And they asked for the diameter, like it will be mm. They asked for the diameter D. So it will be around 8.30 mm. 2R. D is equal to 2R. Is everyone clear with this? Or anything has to be further explained? We can go in detail also. That's not a problem. I'm just
It's clear.
rushing it because of that. Yeah, I'm just rushing it because of the time limit. So answer is sorry. So from the lessons of different spectacular failures, one can conclude that what are the things that we saw, major important things. There will be there will not be any visible plastic deformation before every failure. It's not necessarily true. Is it true? Before every failure, like we cannot say that before every failure, plastic deformation is not there at all. So, but you can say that there will be. So yeah, that is what we that's true actually. The second point is not true. There will be visible plastic deformation before every failure. That did not happen with us actually. There was no much plastic deformation observed before every failure. This is correct, as we have seen whether it can be Liberty ship which had ductile to brittle transition happening, or it can be Aloha one because of stress corrosion, or because this one, Boston or Comet one, everyone, the not much plastic deformation was observed before a failure. The structures made of ductile material fail in a brittle fashion only. It's not true. Structures made up of ductile material can fail in brittle fashion. So this is a true statement, but not it is not true that whatever the material made in ductile, it has to fail in a ductile fashion only. Like as we have seen that most of the ductile material is the one which was used in structural application, but still it failed in brittle fashion. So the factor of safety should be always one. it is always better if we have more factor of safety. But then at the same time, what sir was also telling that it's not like we just simply keep the factor of safety very high without having a proper investigation on the material. So we have to do the analysis. What is a condition that it is going to be present, and what are the stresses acting, and everything we have to see, and then keep this factor of safety properly. It's not like you keep factor of safety very low also, and but not at the same time, we shouldn't keep the factors of safety as 20, 30 also. So that is not true. Every structure or component has to undergo specific design test before commissioning. So this is the reason this is kind of important. You have to see thorough understanding how the material is going to behave with different design or different atmosphere conditions, etc. All these things you have to see before you do the final components, before you put it into commissioning. So these are the right answers. So can anyone answer me for 13th question quickly? I'll just see the chats. Someone has sent something.
Madam, it is C and D.
Yes, it is C and D. It's straightforward, like the factor of safety is 2. And yes, Nitin, it will be lectures will be uploaded like last year only in NPTEL channel after every week. This is anyway recorded. I hope I did press recording. Yes, this is recorded. I'll be uploading this also in YouTube. So this is C and D. The answer is C and D. And for 14th question, we'll wrap it up soon. If you guys keep answers soon. I wanted to discuss further more also, but then I did not expect that I'll be consuming so much time. I'll try to do the time management better from next class. So for question 14, can anyone give me the correct order? Figure A, B, C show. Huh?
CBA.
CBA, correct. Anyway, it's a CBA only. And you guys know how it is done also, right? So I don't have to further explain. But in next class, we'll try to brush up the photoelastics, the basics of that. We will see what each and every terminology mean, so that it will not be difficult for us further and all. And so maximum and minimum stresses in the fatigue are 140 MPa, 8 MPa respectively. The ultimate tensile strength of the material is 550 MPa. Based on Goodman criterion, then the endurance limit in MPa of the material is. So for this one, we will discuss a bit of more the graphs. 37. How many questions are there by the way? Oh, this is the last question. Okay. So when you plot mean stresses versus stress amplitude, you can see that failure can be happening in this fashion, and the points will be in this region. You it will be kind of in a parabolic manner. Every time you will be getting the points in this region in plus or minus. So this is given by Gerber parabola. Most of the failure points will be lying in this region only. So we have to keep the material in such a way that it will be well below this parabola. So different people have given different parabola or lines and all. That's what we'll be discussing, and whatever where it will be what's this called, or endurance limit. So from endurance limit, well, if you try to usually will be fracture will be happening in ultimate tensile strength, UTM, UT, ultimate tensile strength. So if you have a line which will connect between these two rather than a parabola, so that it will all the testing parameters will be well below this line, so that we will be having better safety rather than having just near the failure points. This line is called Goodman line. And each and every parabola lines has different formula. And if you think that like I don't want my material up to ultimate tensile strength and all, I want it to be well below my yield strength. Then when you join the line between the endurance limit and then yield strength is the line which you get was given by Soderberg. Yeah. Soderberg line. These are just to say, make sure that the fracture will not happen by fatigue and the material should be well below the region of working will be in this region. Then it means that it is more safer. So if you want to extend a little bit and then you have to keep it like Goodman line, it means that you're following Goodman criteria type of thing. That's all. So here the question they asked is to find out the endurance limit using Goodman line. So this is not the Soderberg line or Gerber line. So I'm just writing out the formula for Goodman line. So mean stresses by ultimate tensile strength, the whatever its mean stress divided by ultimate tensile strength plus whatever is present in stress amplitude in this y. I'm just writing down the equation of line. Should be equal to 1. This is Goodman line. If at all, if you have to incorporate the factor of safety, then you have to divide it by factor of safety. So right now they have not asked us to do anything regarding the factor of safety. They just wanted to know the endurance limit, and then we can find out the mean stresses using the maximum and minimum stresses that are applied. So maximum sigma 1 plus sigma 2 divided by 2 will be the mean stress. And then stress amplitude will be sigma 1 minus sigma 2 by 2. And then N is factor of safety. And as you all know, the ultimate tensile strength of the material is already given 550. And then you will be getting from this the endurance limit. I hope this is clear. We don't have to, I can solve it, but then the answer will be coming around this one. Like I have the solution written down. But it's clear, right? I don't have to solve it, right? I'm not solving it.
Please solve.
Yeah, sure. We will do it then. What is the sigma 1 given? 140 MPa. Sigma 2 is 8 MPa. And then sigma m will be what? 140 plus 8 divided by 2. This will be 140,
74.
74 MPa. And then sigma a will be 140 minus 8 by 2.
62.
62. 62. 6 MPa. So 74 divided by ultimate tensile strength is 550 plus 66. I got it. And then, yeah, endurance will be E is equal to 1. So if you can just, can stay please. Can someone tell me the value of 74 divided by 550? And this will be 1 minus 66 by sigma E. It will become sigma E minus 66 by sigma E equal to, can anyone tell me 74 divided by 550?
0.135.
So 0.135 E sigma E. And solve it for E. Can someone solve it for E and then tell me what is the value? This will be approximately 1 minus 66. 1 minus 0.135 is how much?
Zero point eight six five.
0.865.
2.865. So sigma E, I think so if you calculate, you'll get the answer like this. You can just someone verify it. 66 divided by 0.865.
It's
That's right.
76.3. Yeah.
26.3. So I asked to give the results in 2 digits, no? So more circle we will discuss in next class. For now, we will stop it. I will discuss a little bit in detail about more circle in the next class. Then I'll not give the introduction in the next class, and then we will have a photoelastic thing also. These 2 things I'll discuss in the next class. Is that fine, or you want me to discuss them only?
You
One
can
general
continue.
suggestion. As you
Yes, yes.
indicated earlier, like for time management, you wanted to compress. So I would suggest like not to compress your sharings. If everyone agrees, maybe the time may be slightly extended.
No, I really don't want to do more than 2 hours. 2 hours is fine for me.
When will
Like
be the next class, madam?
next Tuesday again.
Again next Tuesday.
Yeah.
If
I
it is
hope you.
convenient for everyone, we can proceed with more circle for now.
It's not.
Yes, please, please. We will finish this week.
Yeah, please.
Ma'am
So
is
please
okay. We
proceed.
are okay.
Okay, just giving 5 minutes at least, in like 2 minutes. We will. I have to tell from beginning then. Like I wanted to discuss basics also for more circle. I have actually written 3 pages. If we discuss now, it will go very fast actually. I wanted to show how the stresses also varies along with the with varying the angle. If you try to shift the if you are applying any load, and then if you are trying to
Madam,
shift
if
the
that is the case,
angle.
please move on to the next class only, madam. Because
Yeah,
if
yeah,
you
that's what.
Yeah,
Like,
yeah.
properly explain it in a hurry, also we may not be able to understand what you're saying.
that's what. Like, I want to explain very detailedly, and from next, the reason I don't put everything in PPT, rather I'll write it down, because when we write it down only, like we will be able to explain better how each and every step has happened. That's the reason why I'm writing it down. I can even just put it in PPT, and then this is what happened. This is how it happens. I can tell, but that is not how I usually do the class. So that's why it will take a little bit more
Agree
extra
with your
time.
methodology.
So yeah, but then yeah, I'll try to put it more a little bit in PPT also from next time onwards. But I'll discuss the answers have given anyway. But I'll discuss the mode circle a little bit more detail in the next class. And it's already 8 also. And I really had a very nice class. I was very scared to take this class, to be frank, but you guys made it very easy for me. And please do let me know if I have to discuss any particular topic, so that we will take up the same topic again in whichever your research interest it can be. I understand not just BTech students, other students are also there, with PG students and all. So if your interest is in any particular direction, I can concentrate more on that. So you can write it down in the group we have in NPTEL Swayamvar, that one. So
Ma'am, one small doubt actually.
yes.
So
Good
in
session,
the
I think.
reference material which Professor Ramesh sir had given in the
Uh-huh.
NPTEL website, he
Uh,
refers to one book which he has authored by his own.
yes, yes,
And
yes.
he had mentioned that it is not. I mean, I tried searching for it. I believe it is. I saw one website. It looks very old, but uh, how to download that book? Even if it is on a payment basis, I don't mind because I'm not. I was not able to find a quick reference book for this course.
Let me write this down, this query. I'll ask sir directly only. So they were asking for the book for this one. So probably sir will have some PDF or something. So we'll share it with us, and then I'll share the along with the study material.
Yeah, even because I was ready for buying that book also, but then I believe it is available on a CD, which means that website must be quite old. So
Yeah,
that
it's possible. Even this one, sir, which sir has taken classes way too like years back. So it is recorded, and now we are seeing the lectures because it's kind of one of the best lectures that it is available in India. So yes, I'll talk to sir regarding the references. I'll ask sir to share the PDF or some other format for us so that it will be easily readable for everyone.
thank you.
Madam, this recent, the latest question, that question number 15.
Yes.
Madam, that last, the
Yes.
final thing I missed it. What is the answer, madam, here? That from this I could not make it.
76.26.
76.26. Okay.
I'll keep the I'll even keep this writings also like this only. I'll not delete it, and I'll share just like this. I'll even share the without writing. I'll share with writing, both I'll share.
Yeah, madam. Okay, you are telling some little PPT you can make it, madam. Over that you can write. Maybe no, everything need not be written. Maybe sometimes time saving can be done. Let us suppose here this good man line, this parabola. Anyway, you have to. These things can come in a PPT. Over that you can keep on writing. Maybe that will save
Yes,
some.
yes, I'll try to. Yeah, I'll try to do that. But this was my first class, so I did not expect how much time it will take. And I usually do only 10 classes in 2 hours. 10 questions in 2 hours, but then this was sir kept up to 18 questions actually. So
No, I think every assignment it will be like that.
so yeah, I'll do that. Thank you,
Every
Suresh.
Thank you.
I'll stop the recording now. Thank you so much. We'll meet next week Tuesday.
Okay, so just have one query. As we were talking, you were talking about.
This is general only. Then I'll stop recording 1 minute.
Yeah, sure.